все, что такое. Человек
Хорошо.
может так пробовать.
Хорошо.
Я просто, так сказать, как говорят по-французски, а титр индикатив.
Понятно.
Ну, то есть так, просто некоторые идеи, потому что но какие-то вот, хорошо бы их научить вот именно работать с рядами Тейлора, потому, чтобы они не путались в нахождении области сходимости. Вот. Это вот такой ключевой момент, а дальше все остальное это просто вычислительное.
Ну да, да.
Но пока что мы до этого еще не дошли.
Я понял.
Мы первым делом в следующий раз я как раз про Тейлора расскажу. Мы брали формулу Каши, доказали лемму Азгуда про гомоморфизм.
Okay, so let's consider the first problem, which is the following. So we are given our linear maps from C to C is so L will be an R linear map. So let us just fix notation. So we have on C2 we have two complex coordinates Z1, Z2, and each Zi is can be represented in this form. Okay, so so we need to find C linear and C antilinear parts of L.
So I would like just to recall to fix the definition because I have introduced linear and linear parts without calling them like this. So
okay.
So we know that F, Z are linear. Take the form sum of the sum of AG, ZG plus the sum BG, ZG. And this is C linear. And this is C antilinear. So, if you evaluate it at lambda b, then it is equal to lambda times the same value at b. That means
Yes.
antilinear. Okay. So this is antilinear, but this is linear. And that's
okay, so пожалуйста.
By the way, I can send this similar problem is, but I don't know that the email address so you can send to Arseny, and you can follow.
So what do we need to do? Я что-то не помню, мне вызывать кого-то к доске или как?
You can choose a person at random and ask.
Просто
Да, доске. Хотите доске решить? Okay, so we have this linear operator, and we have to find its linear and anti-linear part. We have to decompose it like this. Would you like to try?
oh, I guess I could try this.
Yeah, sure.
Nice.
Я вот здесь есть.
На каком языке нужно говорить? На английском, на русском?
На английском.
Okay.
Ну, если, да,
So I guess
если вы можете, да.
Sort of. What's the direct formula? I'll just like write something like. Right?
Yes, we need to express x and y via
Right.
z and z bar.
So therefore, I have. Am I right?
Okay, see.
Yes, it sounds okay.
Oh, yeah,
Can you
looks.
simplify it or you're done?
What you can do, you can simplify the expression 1 over 2 plus 1 over 2i, maybe.
Yeah, well, it's nothing but 1 minus I over 2, right? And 1 plus I.
Yes, that's it.
This thing is C linear and this is C antilinear.
Okay, I have a general question. I look here, your operator is defined on C2, but in fact it is R value. So you initialize in the real number. Right?
Yeah.
Is it a general fact that for any real values are linear operator, its C linear and C antilinear parts are complex conjugated?
What?
Are complex conjugated? Is it a general fact?
That for any R linear for any R linear operator, it's now it's not.
Yeah, for any linear operator which takes real values. Because in general it's completely false. Because
Yes.
But suppose that it is not our linear operator. It is not only R linear, but it sends everything to R, to real numbers. Is it true that under this assumption, it's always true that C linear and C antilinear parts are complex conjugated, can be obtained one from the other by complex conjugation?
I guess we
Because here this sounds pretty true. This is
it sounds legit, but I guess I need to check it.
Can you just check it?
Okay, let's check it. We start this need. The question is basically about. It's not important, I guess, if it is C2, we could take it C.
Yes.
So we have. And I know that. So say look at this. Right?
Yes.
And what do we get here? Here. So I guess I could just try to give us this. Up to sign is good.
Yes. Yes.
So therefore, we've got what we want.
That's it. Yes. Thank you.
Okay, so the second example is quite similar to the first one. Okay, so what happens if we take x1 plus y2?
Where it's easier than the first one.
Okay, is someone else willing to do this exercise?
You can assign a person. You can just ask.
Okay, Mish, can you do that?
Well, if we look at the formulas written there and try to say similar for x2, y2 and z2, we get that this is equal to
Okay.
Yes.
Yes. Yes. So just you may regroup the summonds. Yes.
In order to distinguish C linear and C antilinear part, you should move Z2 part to the, in order to put it together with Z1 part. And the bar parts will be on the right. Yes.
Okay, so it's more or less. Okay, so let's do the third case, which is also shouldn't be. Okay, so it's pretty similar. Can anyone do that? No, that's it. Okay, so this is a pretty basic exercise, so let's proceed with the next problem, which is we're given functions of two complex variables. And we need to check their holomorphicity at the origin. So is holomorphic. And the first function will be okay, so what do we need to do in order to check if the function is holomorphic?
Supposed to check the Sherman equations.
Oh yeah, so
Well, we know how this function looks as z conjugate.
I mean, can you just take it directly? I mean, it's a linear function, so it's holomorphic if it's linear, right? If only if it's
Yes, so
Yes.
there is special class of functions which are linear functions. And clearly a linear function is holomorphic, even only if its linear part vanishes. Let's not check. Because for a linear function, being holomorphic is equivalent to being C-linear.
yes.
and equivalently, if not equals C linear, you can see that if we take, for example, 1, 0, and multiply it by I, then that's not.
No, if a function is linear, then obviously its complex derivative.
I mean, linear function is holomorphic if and only if it's linear.
It's C-linear.
Yeah.
Yes.
It's C-linear, yes.
And clearly this function is not linear. I can multiply z1 by I and I will not get what I should get.
That's true. Yes. Yes, that's true. And yes, and the explanation for why our linear function is holomorphic if only if it is C-linear, because it is the differential of the linear function is given as the operator is the function itself. That's it.
Yes. Okay, so this function is not C-linear, therefore not holomorphic. Is that correct?
Yes.
Okay. Okay, so this is not C-linear. Not holomorphic. Okay. Okay, so the next function will be like this. X1 squared plus 2 x1 by 1 plus y1 squared. Excuse me, this is, it's not 2, it's 2i.
And all the signs are plus, yes?
All the signs are plus. Yes.
Can we sort of say that this is a sum of a holomorphic function in something else, and then it's holomorphic if you leave something else is holomorphic.
So,
I mean, it's clearly the sum of z1 squared and 2y1 squared, right?
And what else?
2y1 squared, I believe. Is that right?
yes, that's right.
Can I say that f is holomorphic if only 2y1 squared is holomorphic?
It's unclear because what you do is just, yes, you can do this because z1 squared is holomorphic. And f is holomorphic even if y1 squared is holomorphic. That's correct. Because homomorphicity is preserved under arithmetic operation. And therefore, if a function is sum of holomorphic with something else, it is holomorphic in the addition of something else is holomorphic.
Yeah.
That's
So that leaves us with the function of 2y1 squared.
Yes, this is the holomorphic function.
No?
Not holomorphic. Why? It's the general fact that the real valued function can be holomorphic. Why it cannot be holomorphic?
Well, for example, because every constant homomorphic function in one variable is locally a branch covering.
Yes, it is an open one. Yes, that's true. So if there is a restriction of this function to one variable, yes. But this is actually this is a function in fact in one variable. We have open in principle.
Yeah.
One situation obviously you can do like this. But actually the situation is simple, in my opinion, because if you take a real valued function, then its differential is a real valued linear operator. If you have a real valued linear operator, it cannot be called C-linear. For obvious reason, because it should be invariant with this image, it should be invariant with multiplication by complex numbers.
Yeah, that's true.
Mm-hmm. Okay, so this is not holomorphic as well. Okay, so next example is almost identical to this one at a first glance, but okay, so we have here
So it's that one squared. I suppose.
yeah, so this is clearly holomorphic. Okay, and okay, let me write it down here. So what about function like this?
So it is Z1 plus Z2 divided by 1 over Z1?
Yes.
1 plus Z1?
Can we use like this quotient of holomorphic functions is holomorphic?
Yes, so yes, you're right, that the function will be holomorphic everywhere except where the place where the denominator.
Yeah, obviously.
That's right.
Can we use it?
So,
Can we use it here again?
of course, yeah.
Oh, okay, yeah, but
And
So basically, when you differentiate the quotient of two functions, yes, so this is holomorphic at 0.
Because it is the same, the quotient of function it is the same as function times 1 over function. 1 over function is a composition of the function 1 over z, which is holomorphic, and the function, and therefore it's holomorphic by chain rule. And the product is holomorphic by Leibniz rule. By Leibniz rule applied to real differentials and taking into account that it includes complex multiplication by complex number times differential. If differentials are linear, then
Okay, so maybe let's do the next one also. Which is the following. And here we have so it's z1 squared plus z2 to the third.
And the question is, where is this function holomorphic? And if it is somewhere holomorphic, then where it is holomorphic? On which, so holomorphicity makes sense only on open subsets, and find an open subset where it is holomorphic. It is holomorphic somewhere.
Clearly it's holomorphic at least everywhere except the two lines which are z1 is equal I z2 and z1 is
Can I just come to the blackboard and these lines are important lines. They are called isotropic lines for Euclidean quadratic form. Can you just please write them down?
I can't actually draw them, I believe. Everywhere except those lines are clear on
Yes.
that.
Yes.
The homomorphicity.
Yes.
And the question is whether the particularity in the origin is removable.
It depends because actually what happens is, whether singularity at the origin is removable, but one can ask also the question whether the other singularities are removable or not. Whether a point line on the lines, which is different from the origin, whether it's removable or not.
But there it's clear not removable because the function is unbounded.
Yes. Yes, because what happens is that this is a ratio, is a reducing ratio, and if you take a generic point on the union of these lines, then near this point this function will be unbounded. Yeah. That's the point.
And actually, I guess that shows that it is homomorphic at the origin.
Yes, because it is unbounded in a neighborhood of any point in the union of this line.
Yeah.
Since and since set of those points where you have no cancellation, you have everything is unbounded. Set of those points is dense, is everything except the origin, I think so.
Yeah.
Then at the origin, and since the unbounded locus is accumulated to the origin, then at the origin we have erasable singularity.
Yeah.
Yes. It's not removable. Thank you.
Yeah, so this function is holomorphic on the complement to this, to the union of these two lines. And so what about function like this, which is so the denominator is the same, but now we have in the numerator z1 to the 4 plus z2 squared. So what about this function?
В листочке какой степени четвертой числителя? В листочке какой степени четвертой?
Правда? Прошу прощения. Yeah, so it's sum of fourth degrees. Okay.
I would suggest to look at two problems, with plus upstairs and with minus upstairs.
Okay.
Yes.
Yeah, so what if we change plus to minus?
I see downstairs z1 squared plus z2 squared. The two, yes.
Yeah.
But if we change plus to minus, then we get removable singularities.
Yes.
And why so?
Well, because we can just cancel the factor z1 squared plus z2 squared whenever it's not equal to 0, and then extend by continuity.
Yes.
Squared will be 0.
Yes, so it is.
So it is equal to z1 squared minus z2 squared.
Yes, you can write down that it's equal to z1 squared minus z2 squared. Yes.
Yeah, so here we can decompose this as a product and they cancel out. So we get removable singularities. So we get removable singularities on all these points. So it's a holomorphic function.
And as for the first example, we have to show, we have to check whether there are removable singularities.
Yeah, again.
Yes, here, yes, here. We have to restrict ourselves here to these lines and to check whether points of these lines are removable singularities or not.
The same reason it's not.
The same reason is not, yes, because if you take a generic point on this line, typical point, then it will not be removable because if you are on this line, on a line like this, then you have relations that one is equal to I,
Yeah.
and you have function of one complex variable.
Yeah,
You will have a function of one complex variable. And clearly the upper part will be non-zero.
Yeah, so basically this is not zero under this condition, and therefore you get that the function is unbounded.
Yes.
Okay.
Maybe the next is it to the next integrals to calculate.
Yes, so before the problem with integrals, there is also a problem which is related to this one.
Okay.
So let us look at these functions once again and decide which functions are continuous in a neighborhood of 0. So which of the above functions are continuous in a neighborhood of 0 and separately holomorphic. So again, in a neighborhood of the origin. Okay, A, B, C, D, E, F.
So there's G. Also there's G with minus sign, the last one.
Okay.
Can you use the matrix theorem?
It's too complicated. It's better not to use. But you can use also lemma because it's
Well, so this function should be easy, right? So,
Long as it's clearly not.
Sorry?
If it's clearly not separately homomorphic, the first function.
But here we can use also lemma, which what does as good lemma say. That the holomorphic function which is continuous.
yeah, it has to be holomorphic,
Has to be long. That already.
and this one is not. So it's clearly continuous because it's just linear, but therefore it's not separately holomorphic. Okay, so what about the second one, B?
It's the same, because continuous but not separately homomorphic.
C is homomorphic.
Yeah, okay. Yeah, so this one is holomorphic as well. Okay, so what about these examples? So this one is holomorphic again. So what about these two examples?
Actually, what happens is that partial derivatives do exist. Partial derivatives do exist.
Yes.
But there is some problem with them. Their existence doesn't declare homomorphicity.
Yeah, because well, the existence of partial derivatives, well, it doesn't apply even continuity as a function of two variables.
Yes.
And it's kind of difficult to tell if they are continuous or separately homomorphic since they are not defined in the origin.
Yes, they are defined in the origin and then no chance to have differentiability. So because it's not, they are not only well defined means that here we have much stronger condition that they are unbounded in arbitrarily small neighborhood of the origin. There is no chance to extend continuously to the origin. And moreover, they are unbounded in no neighborhood, in any neighborhood of any point in the middle of this line. And therefore, They cannot extend holomorphically to the lines, and they cannot extend continuously to the lines.
Okay. Yeah, so now the problem with integrals. Okay, so we have an integral over a unit circle of the function sine of zeta plus 1 over zeta d zeta.
Yes, here we have to use one-dimensional complex elements.
You mean the Cauchy formula?
Here it looks like Cauchy formula, but it is
Well, not quite, because we have a pole.
Pole. In Cauchy formula we also have poles.
Yeah.
So it is not Cauchy formula?
It is kind of similar to Cauchy formula, kind of similar.
Yeah.
But you have to tell in which sense it is Cauchy formula, if it is correct.
I mean, is it correct that the answer is something like 2 pi I, right?
2 pi I, that's right. Can you explain? But maybe somebody else. Can somebody else explain why the integral is equal to 2 pi I?
Well, I mean, it is a Cauchy formula for a function sine of zeta plus 1. And, well, that's it. You just got to use the fact that if you divide it over 2 pi a, it's going to be the value of the function
Just
0.
Can you just promote the number?
Yeah, so just write it down so everybody understands.
So, I mean, if we just take f of z sine of z plus 1, then we can, by Cauchy formula, write that f of 0 is 1 over 2 pi I into first one, zeta over zeta to zeta, which is precisely this one. And this, obviously, as sine of 0 is equal to 0 equals to 1. So if we just bring it,
Yes, just multiply both parts by 2 pi I.
There is another way to, because here we have guessed the Cauchy formula.
Yeah, so basically it's Cauchy formula rearranged in a way.
well, you can write it in terms of residues as well.
Yes, we can do that.
Suitable
Yeah.
for any function.
Yes, we can do. We can see in way and also taking into account that the disk of radius 1 contains unique pole of the subintegral function,
Yeah.
and this pole is simple and with no residue, and therefore the integral is equal to 2 pi I times the residue. And residue is clearly equal to 1. Yes.
Okay. So the next one is a double integral. So we have a double integral of the following function z1 plus z2 over z1 minus 1 over 2 d z1 d z2.
The same? Not the same answer, but
The same answer.
not the same answer, but
Not the same. Not the same.
It's here,
I don't think it's also the same.
no, the answer not the same. The answer,
What is that?
I guess 0, right?
That's true. But maybe somebody else can explain this. Can somebody explain why this integral is zero?
I mean, the function is holomorphic by z2, so the integral over... you can just go into one variable
Yes.
complex calculus, and by z2 it's going to be 0, because it's holomorphic inside this circle.
Can you just recall this well-known, this important fact from one-dimensional complex analysis, the integral function of the curve is zero under certain condition? Can you just recall this fact on the language in order to make sure that
Yeah.
no, use the integral is zero.
So this thing is like and then it's integral first one z1 over z1 did z2
We decided, right?
yes, and well, this is a this whole thing is holomorphic in our notation d1 of 0.
Holomorphic in which variable?
In z2.
Right.
This, yeah,
Provided that the one is different from one half.
yeah. Well, and so this is 0, provided that one is different from 1/2.
Can you just state the series that the integral of holomorphic function is zero? Can you just state the statement? In full generation.
In full general. Okay.
Just in the case of when the curve is bounces in the connected domain, so just in this very basic case.
Yeah.
With smooth boundary,
Do we need a condition of smooth boundary?
with piecewise smooth boundary. Because you have to integrate along the boundary, right?
Yeah, but it's like it's if you wanna prove it in one-dimensional complex analysis by using a Stokes theorem, then yeah, you have to use the condition of smooth boundary. But
Let us write it down.
Yeah, so we need some condition on the boundary. So usually it is proved just by piecewise linear something, triangles, something like that.
Well, yeah, but in general it can be just a Jordan curve. And then it's proven in one-dimensional complex analysis, but everyone forgets about it eventually and just uses Stokes theorem, and then they have to demand smooth boundary. So yeah, use it on a simple connected domain with smooth boundary. Yeah, yes. Holomorphic holomorphic. F of the boundary is 0.
That's it, same thing, yes. And what you do is you apply this theory for function in one variable, namely it's a variable z2. And your view is just unit disk center.
Yes.
And hence the integral in the bracket always vanishes.
Yes, so just the subintegral function
Yes.
under this integral vanishes by this theorem. Okay. So one more similar example will be
Well, we would say that z1 to 2 is equal to, well, z1 is equal to plus 1.
okay.
And then we have that we have 0, 1/2.
Is it 3 or 4?
Excuse me?
It's the with.
3 четвертых, 3 over 4. Let us see. What about 2 pi r? It's
No.
So here's the expression. So we have that this is 3 over 2 times 3 pi I squared all
So how do you calculate this integral? So Cauchy formula. Okay, Cauchy formula. That's it. Then this is the value is here. Is this right? Yes. Okay. Okay. And therefore, this integral is equal to.
But do you need to multiply by 2 pi r squared? Yeah, multiply, not divide.
Okay, no, here,
Yeah, here it's correct.
yeah, and then we
And
multiply both of them.
upstairs you have to multiply.
Yes. Okay, then should like this.
Yes. Yes. Exactly.
Okay. Okay, maybe let's do the final one. So as you can see, this is again a cleverly disguised Cauchy formula. And the final one is, so it's again a double integral of cosine zeta 1 minus 1/2.
I believe.
Oops. Yeah. Yeah, so this is, this is important.
I believe it is 0 because we can use the same trick to split the integral by Newton's theorem.
Yes, maybe somebody else could answer this question. Maybe somebody else, except you, three of you, answer or explain why it's integral 0. Yes, please. But I have a question. In the Cauchy formula holds provided that the point Z, where you evaluate the value of lies in the polydisk, right?
Yeah.
Does it, in which polydisk do you work here?
There.
Yes, polydisk of multiradius 1 and 1/1/3, right? Does this polydisk contain the point equation, a point 0, 1/2? Does this point lie in our polydisk? Because in order to be able to apply Cauchy formula,
Z2 is part of Z2 is not.
sorry?
Part of Z2 is not inside it.
Yes, Z2 is not inside the disk of 1/3. It is not inside, and therefore we cannot apply Cauchy formula here. We can't apply the Cauchy formula as it is for this polydisk.
Yes.
We have to use some other trick.
I forgot difficult about this?
Actually, you have to just to look at this function and to try to integrate it somewhere. Integrate it somewhere. So I suggest that you integrate it along the Z2 variable. Because what is the problem in our case? The problem is with the Z2 variable, right? Maybe it's useful to integrate in Z2 variable first, because by Houdini theory you can integrate first in Z2 and then in Z1. And would like to try to integrate along Z2 variable.
How to do that?
Oh, we can expand with the sum.
Expand this one?
Yes, you just you first integrate in the Z2 along the boundary of the disk.
Also, I must like to extend the cosine at one.
Yes, you just use it for Houdini theory, you just permute the variables, the Z1 and Z2. Here we can do it. But I suggest that you integrate in the following order. First, you integrate in Z2, and then integrate in Z1. Let us make the first step integration along the boundary of Z2 disk.
I also forget how to explain the Tyrol series. And somebody help me.
Because when you integrate along the Z2 variable, then Z1 is constant, right? You fix Z1 and you vary Z2. And we integrate in Z2. Right? You treat Z1 as constant and you integrate your function in Z2. Along the boundary of the disk in Z2 variable. Along the circle of radius 1/3, something in the origin.
So you may write it as a function of one variable, of Z1.
So let us denote cosine Z1 as A.
Okay. Okay, so so it suggests to do the integration
Along Z2. First along Z2. And what is Z1?
Okay. So how to?
We can erase the second integrand. I would like to suggest this is very just along the second variable. Yes.
Okay.
Yes, you integrate along the second variable running along the circle radius of radius 1/3. Okay. Plus 2. And you multiply it by the Z2. Okay, the question is, yes, somebody remarked correctly that this integral should vanish. Can we explain why this integral should vanish?
Because the denominator is not the block.
Because the denominator is not. Yes, you're right that you may have to examine the denominator because the numerator is fine. It is holomorphic in the disk equation. It's perfectly fine. The only problem may come from the denominator.
Yeah, so here this is a constant, we treat this as a constant, so the only pole
Yes, a pole
happens at
zero, zero, the denominator, it is a pole of the function, it's 1/2, right? And what can one say about the behavior of this function?
It's not defined at the points.
Yes, it's not defined at point 1/2, yes, that's right. But is it well defined in the disk of radius 1/3? Is this function well defined in homomorphic in the disk of radius 1/3?
Yes.
In order to check this, we have to examine whether the point 1/2 lies in the disk or not. Does it lie in the disk? Does not lie. And therefore, the only indeterminate point, the only singular point, lies outside the domain equation, outside it. And therefore, our function is perfectly holomorphic in the disk of radius 1/3, including the boundary, basically. Because the point 1/2 doesn't lie in the boundary. Therefore, what we do, we integrate perfectly function holomorphic in the disk and enclose the disk along the boundary. And therefore, we get 0 by this theorem. This theorem, implies that it is 0. Because we integrate holomorphic function, holomorphic in the disk, along its boundary. What is it?
Okay, so the next few problems are about Taylor series, so we're not going to do them just yet.
What are they about? Exactly, because maybe we can write down some kind of Taylor series if the problems are not that tricky.
Yeah, so the first one is just to write Taylor series at the origin and to find convergence domains.
No, convergence domain is tricky. We have to wait.
Yeah, it's yeah.
Okay.
The Cauchy-Demarche formula? There is something else than the Cauchy-Demarche formula?
Exactly, yes. There is a version of Cauchy-Demarche formula for the Taylor series of functions for many complex variables. There is a version.
We know the Cauchy-Demarche formula.
For one variable, right? For one variable.
No.
I believe that you know it for one variable.
It's not sufficient to know it for one variable to start with the truth.
But actually, yes, but there is a generalization of Cauchy-Demarche formula for many variables. That's right. We will see it next time. But at the moment, what I can do right now, we can deduce. So I had to talk to deduce existence of Taylor series from Cauchy formula.
So I do need here in this exercise the Cauchy-Demarche formula to find the domain convergence.
We have to find to use a generalized Cauchy-Demarche formula and properties for convergence domains. Зараз properties for convergence domains.
Like it is a polydisc?
Sorry?
Like it is a polydisc?
No, it is a union of polydiscs centered at the origin. That's it. And we will see it next time.
Yeah, but the union is possibly infinite.
Yes. So, what we can do right now, because we have still a lot of time,
Yes, on 10 minutes.
I can suggest to do the following. To do a part of lecture as an exercise. Namely, to take Cauchy formula and from Cauchy formula deduce decomposition in Taylor series, in convergent Taylor series. Yes.
The convergence domain.
Just you have to choose to show that if the function is holomorphic in some domain, then at each point, in small data from each point, it can be represented by convergent Taylor series. I can just make small first step of this, yes. Yes, O, calligraphic means holomorphic.
Yeah, so F is holomorphic. Okay, so what you suggest to show is the existence of
Octagonal series, что each point has a neighborhood where the function can be represented by conversion error series.
okay.
There exists a polydisk.
Such that F
F of z is equal to sum of the series. Sum of ck times z minus x power k. Then z minus x power k. Now k is k1, etc. kn.
yeah. It's a multi-index.
It's multi-index. And kj are non-negative. Kj are integer non-negative. That's it.
Okay.
And let us write down what does it mean multi-index power. Multi-index power. Z minus x power k means z minus z1 minus x1 power k1, etc. Z1 minus x1. Yes.
Yeah, like that. So it's a product of n.
In complex series, it is way better to avoid using index I.
Okay, yeah, J. Cj minus xj
Yes.
to the power kj.
Yes. So the first step, the first step would be to show that this holds in any polydisk, and I can you. So this holds in here. That's it.
Yeah, for all of that.
Yes, and moreover, we can. It is enough to choose a polydisk whose closure is contained strictly here, and then the composition works here. That's general setting. And then we outline the special proof. So x, let us consider that x is the origin, because we can shift the coordinates. We can consider that x is the origin, and we can have to show that f of z is equal to ck z power k. That's what we have to prove.
Yeah.
And we will use Cauchy formula. We know that f of z is equal to 1 over 2 pi I power n. The integral f of zeta divided by product of zeta j minus zeta j, that zeta 1, etc., that zeta n. Here it is, the Cauchy formula. And first of all, my suggestion is the following: to make Taylor series for the sum-integral function. Make a kind of Taylor series for sum-integral function using the following trick. 1 over zj minus zj. So what we know? We know that the modulus of zj is equal to rj. It is strictly bigger than the modulus of zj. That's important.
Okay, yeah.
Yes, that's important. And then we can, next step is the following. We can write down 1 over zj, and here in the brackets we write 1 minus zj over zj. That's it. And now let me assume the fact that zj over zj, the modulus of this guy is
It's less than 1. Yeah.
That's important. And therefore, this fraction decomposes in Taylor series in powers of this zj. That's the starting point of proof that everything is decomposed in Taylor series.
Yes, just some of
Yes.
how it's called geometric.
And we can write down the guy as following. 1 over zj times sum of L from 0 to infinity zj divided by zj n. That's it. It's preliminary Taylor series. And we can do the same for each j. For each j we can do the
Yes.
same. We can multiply this the Taylor series as obtained. And we obtain Taylor series for the symmetrical expression as a Taylor series in Z. And afterwards, we have to integrate the Taylor series and to show that the integral of the Taylor series is again a Taylor series conversion is a conversion Taylor series. That's it. And this is very straightforward by the same measurement principle as was seen before. Because what is the coefficient here? The coefficients is f of z. Is a bounded function, bounded by some constant n.
Yeah.
This series is absolutely convergent. We multiply absolutely convergent series with a uniform bound or convergent rate because we can confine z in smaller disk, in smaller poly disk. And everything will be uniformly convergent in the smaller disk. The series will be uniformly convergent. And product of uniformly convergent absolutely uniformly convergent series is again absolutely uniformly convergent series. And if the sum of the modulus of the series is bounded by constant, then no problem to integrate it and to the integral is again that's the end of proof. So now we can prove important theorem that every holomorphic function locally decomposes as Taylor series, as convergent Taylor series. And moreover, the series converges on compact subsets on any polydisk whose closure is strictly contained here. So that's all I wanted to say. Is there some exercise about Taylor series? And we will do this in details in the beginning of the next lecture. And with explicit formulas for this constant ck in terms of both integrals and derivatives.
Yeah. So the next seminar will be about Taylor series. Okay.
So, we should finish. Thank you very much.